Hi there. Oh, everything in the right order, right? Hi there. So, we haven't done a lot of presentations lately, and I'm a little bit out of practice already. But do I look into the camera with my squinty eyes? Yeah. Oh, I need a lubricant. Well, we talked in previous presentations about igneous rocks, plutonic and volcanic rocks, basically. And some of that stuff, volcanic ashes that blow out of volcanoes, and like cinder cones related materials. And now it's time to talk about metamorphic rocks. And I start out telling you from the beginning, I'm a sedimentologist, I'm a soft rock guy. I'm not an expert in these metamorphic rocks, but I want us all to be more or less at the same level of basic geological understanding. So that is what we're doing here when we talk about geology for engineers and for whomever else might be interested in this process. Metamorphic rocks. Well, I stole it from a book to refresh my memories from my early geology days. And this was a book that was recommended to my daughter when she studied geology. And it's titled Earth, Portrait of a Planet. And it was written by Stephen Marshak in 2005. Okay, so if you want to have a hard copy presentation on this stuff, go and read the book. We're going here to this blah blah, this cartoon from Lisa Gardner that we have used throughout the show. And now we're going to talk about metamorphic rocks. And those rocks occur often around intrusions or volcanic pipes with hot magma in it, right? That heats the rock up around it, and typically also at higher depth of burial, so they have high temperatures and high pressures. And those are called contact metamorphic rocks, right? You can also be near a subduction zone where the oceanic crust dives often below the continental crust. And the friction here can be damn high, right? And it can be so high it melts rocks, and then you're creating plutonic rocks. But here, at somewhat more moderate temperatures, it's still pretty damn hot, to be honest. I wouldn't put your finger there. Right, that is where metamorphic rocks form, and of course these rocks get crumpled together in these subduction zones, and we call it sometimes prismatic accumulation, right? And that also is a pretty specific environment where metamorphic rocks are formed. So metamorphic is so surprising. A Greek word. These Greeks, they were pretty smart. So meta means beyond the original rock, or changed rock, right? And morphe is they have changed in another form. They're metamorphosed. Oh yeah, I need a pointer. A metamorphic rock is a rock that forms from a pre-existing rock. Aha! Or protolith. Protolith. When the protolith undergoes mineralogical and textural changes in response to its physical or chemical environment. So this is not a sedimentology environment. We're talking about heat, pressure, and chemical thingies that happen in the subsurface. And that creates metamorphoses. And these changes occur when the protolith, the original rock, is subjected to heat, pressure, differential stress, when movement occurs along fault systems in the form of pushing and pulling or shear. And also you can get zones, especially along faulting, where you get hot water solutions moving along the fault plane or along fractures or along volcanic pipes, and those things are called hydrothermal fluids, and they can also cause metamorphosis. Not surprising. So one of the critical things you have to realize about metamorphosis and metamorphism is that we're dealing with a solid state process. It does not involve molten rock. Well, a little bit, but overall, in broad terms, it does not involve melting and then coming out of the melt as new crystals, right? It's a solid state process. The rock doesn't flow typically. Characteristics of the protolite often remain recognizable. So if I had some sedimentary structures, then I might find them back later on, maybe deformed, but I may find them back as in metamorphic rocks. Interesting. And metamorphic rocks have a certain metamorphic texture, and that is formed by grains in the rock that have heated up, recrystallized, and grown in place. And while they grow, right, they start to grow into each other and interlock, forming very typical textures, right? And those metamorphic rocks can contain metamorphic minerals, minerals that only crystallize and grow, right, under metamorphic conditions. Metamorphic rocks can have metamorphic foliation, i.e., the parallel alignment of platy minerals, such as muscophytes, right? And or the presence of alternating light and dark colored layers. And I'll show you an example of that when we talk about gneisses. Nice. And you have to realize that those metamorphic processes can take place over a very long time period. It can be short, relatively, a few thousand years, but often it stretches out for millions of years, right? And then what comes out on the other side, you barely recognize as, oh, that was a sandstone. So here are some common metamorphic processes that are active during metamorphosis. And one of the first things is that when things heat up and get under pressurized, then the shape and the size changes. The crystals, and maybe it was a quartz grain, nice and rounded, but the high temperatures and the pressures cause it to recrystallize, and it takes on its old crystal size, right? Or you can change the face of the mineral. It's the same composition as it was before, but the crystal structure has been changed. That's a phase change. Metamorphic reactions or neocrystallization. It doesn't need to be completely staying the same mineral composition. If you have a combination of, say, those hot water fluids or other chemical reactions together with the minerals that are subject to this metamorphosis, we can get neocrystallization. A new mineral can develop. And that new crystal can be quite different than the ones that we encountered in the protolith. And then we have precious solution. That starts already during diagenesis, where you get a grain, right, heavily pressured at a contact with another grain, right, and that point contact experience very high pressures from the overlying rock weight, and that combined with, say, some increased temperatures can result in the dissolution of part of that mineral along those contacts, and that solution can go to an adjacent pore which is protected from the weight of the overlying weight column, and there it would come out of solution and precipitate as a new cement. Right? That is the process of precious solution, and examples of that are stylolites that you can see in limestones. Right? Plastic deformation. Well, if something heats up, typically it gets a little bit less brittle and hard. It becomes more plastic, and then you can easier deform it. So we get plastic deformation. It's quite common, and I'll show you an example of that later on. So metamorphic rocks occur in certain rock types based on their texture, maybe. We have two main groups of rock types: the foliated metamorphic rocks and the non-foliated metamorphic rocks, the layered ones and the non-layered ones. So foliated metamorphic rocks have its minerals and thus its layers or laminae reoriented perpendicular to the differential stress that the rock experiences, right? Due to shear stress, for example, in a subduction zone, where rock moves and gets dragged below the continent, right, in the subduction zone. And it can cause a lot of shear stress, and then it can cause mineralization there. So here you have a protolith clay or shale bed, right? And it gets heated up somewhat, and the minerals, often the micas, they start to be oriented parallel to the bedding here, or perpendicular onto the direction of maximum stress, and form this cleavage here in the rock. There you see the bed layers or the cleavage layers, right? And it creates a very plated, coarse platy rock, because the metamorphic processes are not that far advanced. So that is slate, and shale, when heated up, can form slate. And you can get a slate kitchen counter. Or it gets a bit more platier, and you get more minerals that grow in size, right? Like the micas get larger and larger, and parallel bedding create or aligned parallel to the maximum stress, to the direction perpendicular to maximum stress, right? And creates this kind of layered rock, a phyllite, which is in some ways more a higher grade metamorphic rock than the slate itself, right? Maybe more sandy. Here you can have a sandstone that is with a lot of clays in it, and it becomes more coarse. It is coarser grained than, say, the shale originally, but still it gets this foliated, bedded layering in it, right? This is called a schist. And if things start to really recrystallize and melt and getting deformed, then in a high form of metamorphosis, we can a gneiss being developed. And then I like to be funny and call it a nice gneiss. Right? This is a nice gneiss. Looks nice. Right? So how do these gneisses form? Well, here is a way, and then, I mean, we were not there, so it is always a possible method. We think that a gneiss may form, or one of the ways it gets formed, using a combination of shear stress. And you need to be in a tectonic zone with movement then, and with recrystallization, right, where you get creating the banding of quartz-rich bands and dark mineral-rich bands. And you can start out with a simple rock with shales and big clasts or pebbles of sandstone in it, right? And they get then pulled apart by stress and movement along a fault plane, say, or a zone of deformation. So it gets pulled here to the right and there to the left. And what does that do? When you have a square rectangle and you pull it in opposite directions, you get a trapezoid, a flattening of the rock. And then these rocks, these pebbles inside, may become deformed and form light-colored semi-bedding inside this deformed rock. And it can go even further, and you get folding of these rocks and more flattening of the original components of the rock, and ultimately it can become a gneiss. And then millions of years later, I stand there at the surface with my little pick hammer and in the glaring sun, and I try to take a piece of rock from this gneiss, and it is bloody hard. So I'm sweating like a you know what. Okay, and then you can go even further, and it melts, or part of the rock melts, right? Now you have here the protolith, and then inside it, there you got a melt that then cooled off again and formed this migmatite. And looks there more gneiss-y like, and there that might look like a gneiss, but you get a lot of deformation and melting, and we call that a migmatite. Sometimes it can be quite messy, like in this close-up, right? And this is also an example of migmatite, right? A lot of movement, a lot of banding, gneiss-like, but now it actually did melt and cooled off again. And so that's a partial melt, a migmatite. And we talked about fault planes and that there is a lot of shear stress along the fault plane. And if that starts to happen, you can get some striation or bedding or foliation along the rock, along the fault plane, and minerals can be elongated and deformed along that rock and form a mylonite. Right? And of course, we can just heat the rock up and we get a homogeneous rock. We call that non-foliated. Here you have a piece of rock, maybe basalt, right? Or a sandstone high in dark mineral content, and it forms then upon heating and high pressure, mostly heating though, a rock high in hornblenders typically, and this is called a hornfels, a German word. And you can have had basalts like this one, and it is changing in recrystallizing and becoming high in hornblende, an amphibole mineral, and feldspar, and then forms an amphibolite, very similar to a hornblende in composition, but it might be more formed under higher pressure. Or you can have a limestone that heats up and recrystallizes, and maybe with a little bit of iron in it, and it becomes this red colored marble. Or if it's less iron, it might become a nice marble that you find back again on your kitchen counter or your bathroom counters. The same can happen with quartz, with sandstones, right? A little bit polluted or contaminated with other minerals, and you can get this quartzite here, or this much less polluted quartzite in the lower right. Woo, woo. So you start to realize that the protolith composition is quite important when dealing with metamorphic rocks. If you had a shale that is very fine-grained, then it may form a fine-grained or politic, not politic, no politics today, this is just geology, politic or peloid, politic metamorphic rocks, right? Or if it was a basalt, then you can get more basic metamorphic rocks, or mafic. You remember that from the igneous section, right? And so it is typically high in biotite and when low pressure hornblenders and other amphiboles, right? That's a basic metamorphic rock. And you can have another protolith, limestone, and you can get calcareous metamorphic rocks, or quartzo-feldspatic metamorphic rocks, right, from an old granite, or a sandstone that was higher in feldspar content and not so high in dark or mafic minerals, right? So quartzo-feldspatic metamorphic rocks, calcareous metamorphic rocks, basic or mafic metamorphic rocks, and pilitic or fine-grained metamorphic rocks. We're going here into developing a metamorphic rock classification, and of course the degree of metamorphosis is very important. So we're looking at the metamorphic grade here, right? And I mentioned diagenesis. That is the process where you go from early burial, just after the sediment was formed, right, to deeper burial, sometimes several kilometers deep, with high temperatures, but not exceeding 200 degrees Celsius. Those processes typically make loose sediment into a sedimentary rock, a sand into a sandstone, a lime into a limestone, a clay and mixture of quartz grains into a silt, right? And that process is called diagenesis. And the cementation of that rock is called lithification. But if you go above 200 degrees Celsius, we're entering the temperature ranges of metamorphic rocks. Rocks start to recrystallize, right? Neocrystallize, or growing, or they start to nearly melt, right? So low temperatures, we have 200 degrees Celsius to 320 degrees Celsius, that's called low-grade rocks, low metamorphic rocks. When we talk about 320 to about 600 degrees Celsius, we call that intermediate metamorphic rocks, and high-grade metamorphic rocks is everything over 600 degrees, all the way to the magma chamber. So we can put that on little graphs, right? You have here pressure, and there is temperature, right? And then here below 200 degrees and low pressures, we get often non-metamorphic rocks found. And then here at higher temperatures, we can get low-grade metamorphic rocks or intermediate metamorphic rocks or high metamorphic rocks. And then if you go even in higher temperatures, typically over 1,000 degrees, you're entering the realm of igneous rocks, right? Magma, lava, that kind of stuff, right? And so an example of a low metamorphic rock is typically a slate or phyllite, right? And in the intermediate realm, but at low pressures, we can get hornfelses. It depends, of course, on the composition of the protolith as well. So if you go to the lower part of this graph, right, you can have here the protolith being a basalt, for example, often highly mafic, high in dark minerals, or you can have a shale, very fine-grained, pelitic metamorphic rocks, and a pelitic shale, right, fine-grained sediments. And then when they heat up from 200 to 300 degrees rock, then we're talking about low-grade rocks, and sometimes these things become schists with a lot of green minerals in it. We call them green schists, right? If they get high in amphibole content, we call them amphibolite, right? Or hornfels. And then here you can get mafic, dark-colored granulites, right? So if you have a basalt here, right, that can have typically minerals for the low metamorphic grade that are zeolites, chlorites, and then here in crossing the borders a little bit, epidotes and amphibolites, right? And then we can get garnets in the higher range, the high grade metamorphic rocks, and pyroxenes. Yeah? But you need a protolith of basaltic-like origin to get those mineral assemblages. Yeah? And shales might develop into slates and phyllites, schists, right? And gneiss there. That's typical low-grade shale. And then if you look at the mineralogy, then they can be clay, all kinds of clay minerals when they are shales, but they alter and become chlorides, and quartz and feldspars often recrystallized or neocrystallized, right? And then they may develop at higher temperatures muscovite and biotite, the more classical micas, created from clay minerals and other phyllosilicates. And then they start to become garnets, staurolites, and kyanites. And at the highest temperatures, they may develop into minerals such as sillimanite. So you see that we can get these different associations of minerals based on the protolith, but also based on the degree of metamorphosis. So we can look at a series of index minerals that are typical for certain temperature and pressure regimes, and also, of course, dependent, as we saw in the previous slide, on the protolith. These index minerals, they indicate the approximate metamorphic grade of a rock, right? So you can look at the occurrence of chloride. Before you had sedimentary rocks and you had 200 degrees Celsius or less, but now the temperatures go to low-grade metamorphic zones, and now we find the first occurrence of chloride. And so you can say that once chloride shows up in the rock, and you can put in a mapping area a position where that transition occurs, where the chloride first appears, then you can make that into an isograde. One side of the isograde or contour line is diagenetic and non-metamorphic rock. The other side sees, as indicated by the chloride that suddenly occurs. And so now we are in a chloride isograde. And you can go deeper or to higher temperatures, and then you can get, say, I don't know, pyroxene being formed or garnets. And the first occurrence in an area of the pyroxenes, say one side is first chlorides and the other side of the line, a spot on the surface where you're mapping, shows all of a sudden pyroxenes occurring, then, well, that is the pyroxene isograde. And then the zone between the first occurrence of the chlorides, the chloride isograde, and the pyroxene isograde, that area in between, is called a metamorphic zone. A metamorphic zone is a region that occurs between two isogrades. The zone is named after an index mineral not present in the adjacent zone. Say the pyroxene zone on one side, but if you go on the left thereof, then you only find chlorides. So the pyroxene is not there and it is chloride dominant. So now you call that the chloride metamorphic zone. So that's how we map metamorphic rocks. You can see here a metamorphic map with the different zones here, and this yellowish stuff here is below 200 degrees Celsius when it was formed based on the mineralogy, right? And we call that the unmetamorphosed zone. And then here, when we exceeding 200 degrees Celsius, the rock may develop all of a sudden chlorides, right? And this is then the chloride isograde. And then if you go deeper and higher temperatures, you may form biotite. The chloride muscovite zone and the biotite zone are both low-grade metamorphic zones. But now we go into an area that was exposed to higher and higher temperatures, and now you can recognize an intermediate to high metamorphic garnet zone or staurolite zone, or an area where first here's the sillimanite isograde that bonds the sillimanite metamorphic zone, which is high grade. You see, we're getting a feeling for what you can do with metamorphic rocks. So you can subdivide them in different phases based on temperature gradient, that the depth that they were, the pressure that they were exposed to, and maybe the composition, right? So here are these lines, right? They represent the geothermal gradient. And if you are on, say, very thick parts of the continent, then of continental crust, you can get pretty high continental temperature gradients. If you're near a volcano, yeah, you can get like here in number 3, you can, or sorry, in number 2, you can get a volcano arc type of geothermal gradient, and that tells you at what depth and therefore at what pressure you typically get 400 degrees Celsius, and you can get typically a green schist metamorphic facies, right? And of course the protolith, the protolith also provide some input in the composition of the mineralogy, right? Here at 5 we have a accretionary prism, which is inside a subduction zone, right? The collisional mountain belt is something that is more typically adjacent to the subduction zone on the continental crust plate side, right? And it can get pretty hot there because you have all this friction and pushing together of the rock there, forming an orogenic belt of mountains. At the same time, you have a lot of friction going on below it, which heats it up even more. So that can, especially if you're near the subduction surface itself, you can get pretty damn high temperatures there in that accretionary prism, where all the rocks, sediments from the continent, and oceanic crust from the oceanic side of a subduction zone are pushed and crushed and mixed together, right? A metamorphic facies, like the green cyst facies, is a set of mineral assemblages formed at a certain temperature and pressure range. And a mineral assemblage is a group of minerals formed from a specific protolith at certain temperatures and pressure, right? So these are the terms you want to keep in mind. There are your gradients, and those are and they are associated with various settings, like a volcanic arc or a stable continent but very thick continent, and so on. Mountain belt. So here we see something that we can call environments of metamorphosis, right? You have here above the hot mantle, you can get contact metamorphosis when you go deeper into the rock, especially if your temperature gradient is increased because you're near a subduction zone, right? Where you have your prismatic accumulation or accretion, where everything, sediments and ocean crust are thrown together and then crumpled and distorted and heated up when it dragged towards the mantle into the subduction zone. Right? And you can easily understand that you can get different facies, right? Based on the protolith, there you could get oceanic crust that metamorphosed into a blue schist. If you had a shale, right, in there, and here is the sediment that were washed in, right, along the shoreline, and so there you have low-grade shales, just not much more than diagenesis taking place. But when you get deeper and the temperatures get higher and the pressures increase, you can make it into shale, slate. It can evolve into schists and even gneisses when you're really high and deep temperatures. So if you go at our accretion prism, you might notice also that there are local intrusions there that create contact metamorphosis, not only when you go from the mantle into the overlying crust, but also here along the sides of these intrusions, right? These magma chains. If they're shallow, right, it's low pressure and high temperature. If they're deeper buried, they are high pressure and high temperature, right? So if you have just a tiny bit of thickening there and burial, but near the subduction zone that is creating high temperatures, you could get some kind of a schist being formed or a slate, and you can still see relic bedding in there, right? And other sedimentary structures that kind of partially been preserved. Now we're going a little bit higher pressure, maybe a little bit deeper and higher temperatures, and you can get schist. Or you get high temperatures here and high pressure, and you're creating a lot of movement here, and you can get the development of gneisses, right? Or there, when we're getting so hot near this Pluton, you can get partial melts and create a migmatite. If you have an intrusion here at relatively shallow depth, you can get the development of hornblenders, right? Hornfells. Or you have a lot of friction along these faults here in this orogenic belt of mountains, just adjacent or above the subduction zone. Guess what? You can create mylonites along fault planes. So, depending on the rock type that you develop, you can kind of figure out what grade of sediment metamorphosis you're working with, what the protoliths were, and what kind of an environment, right? Prismatic accumulation or just plain contact metamorphosis, what kind of an basically metamorphic environments you have. And I showed you how you then can convert, interpret that also from how you map these different rock types. And with that, we're stopping. That's kind of all I'm going to tell you about metamorphosis, metamorphic rocks. And really, I mean, apart from that they have nice ores in them, or can have in them, or they can have veins around them with ore in it, or right? Gold, silver, all that stuff. So it's the realm of the hard rock geologist. So from that point, it is very important. But if you were looking for hydrocarbons, most of that stuff has burned up and is completely destroyed, right? And so we are much more interested in diagenetic processes and sediments where we can get preservation of the famous and much beloved hydrocarbons.